Everyone's going sideways. But like one is off that. And then place for
so these food parts will also be used, so you can see that for these. I think they took it maybe to the library.
no, but this still has to do. That's okay.
She said that you
Yeah, but you don't need to fix it. If you can just read it from the visually, the value at the lowest from the data. You can just read it from the Excel data. It's fine. So no fitting, just
and just like.
yeah. We don't need more than one measurement. It's just a verification. What is the measurement after so many hours?
Feels stupid.
So you can.
Okay.
I would say measure
Right.
every one of them. Three replicative measurements, one after another.
It's also process.
In the first hour, and then it's yeah, something like that. Okay.
The BG. Also,
This is a low coaching. Also not exposed. This is more plastic exposed and is not exposed. Yeah. Those can do much time on it. The Russian saving. Otherwise, you have to realize it. And hopefully we get the double value there.
Just take a bit more time. Reading this website.
Yeah.
Yes, I always have this same.
So they will also the net loss is legal. So they will not be. Not everything
To report the real start. So Brad is taking picture of the previous moves. No, I think we want the cars. I don't think it will be because this is USB. That's USB-C. We have one of the selected. We have those smart
like you someone.
I actually have some.
And this day was
No, it's just. I will make sure you can change the
No, but okay. This one selected and then
Yes.
when yellow was playing but like I think it's very second forward. Like over when I was
Concentrate.
Reasons.
That's the right question for you.
That's a very fun question. You know most it's
The portable one. Yeah.
that's on the ninth floor.
Yeah.
Do you know something about the errors or not?
Yeah.
Because I get an error that the level is too high, but also that it's too low. So yeah, I try to refill it with weeks. I mean, if it's low, it was by the
Yeah.
it was yeah, back in on the but yeah, but that's why I'm trying. I have to check it. I thought maybe you had simple. Something shady because you can say to your system, and it's necessarily whatever. It's still low. Yeah. Okay. I'm really impressed with that one. That you
See, but if
We are waiting for the connector.
we're trying to I think what's for that is pretty good. Myself.
Well, I think that's about it.
Yeah, like singers.
No, how can you fix that? Just the server and the speed on serve.
Which one get later?
How do I increase the volume? The volume. It's a MacBook. How should we increase the volume? Yeah, if we can tell them
Aliona, can you hear me?
Yes, yes,
Okay, fine.
I can.
Okay. Morning, everyone. Morning. Sorry, we are a bit late because of the technicalities. Welcome to the scientific session, and today's the webinar series from the NICKEFFECT project. Maybe Ms. can already introduce.
Good morning, everyone, and good morning, Aliona, and welcome to the scientific session. It's an honor to introduce Dr. Aliona Nicolenco. She's going to be the speaker for this scientific session in the framework of NICKEFFECT project. Aliona holds a PhD degree from University of Vilnius, and she had also completed a 4-year postdoc within the framework of Marie Curie's grant, and she is now a senior scientist at CIDETEC working on energy storage and energy conversion materials. And her today presentation is going to be industrial application of electrodeposition process. And without further ado, I'll give the floor to Aliona.
Thank you, Mespin, for this very nice introduction. And thank you everyone who could join this webinar today. For me, it's really a pleasure and honor to give this presentation, and I hope you'll find it interesting and useful. Before we'll go to the content of the webinar, just a few words about my institution. So CIDETEC is a technological complex that consists of 3 centers. This is CIDETEC Surface Engineering, this colorful building here, nanomedicine and energy storage. And we are located in the very beautiful city of San Sebastián in the north of Spain, just next to the border with France. So I'm working at CIDETEC Surface Engineering. This is actually the only center in Spain that is specialized in surface technologies. So we have more than 4,000 square meter area of the facilities and the laboratories, which are equipped for the fabrication of different kind of materials and also their characterization and testing. But I have to say that we are not really an industry, so we are somewhere in between academia and industrial sector. So we have a lot of R&D projects where we develop innovations for the future industrial application. Then we also work on the technology transfer, where we help our clients to adapt the processes according to their specific requirements. And we also offer different services to the clients that can be the characterization of the materials or the problem solving, evaluation of the process on site, prototyping, and so on and so on. And I would also like to say that we really like to welcome university students at CIDETEC. So if at some point you are looking for a place to do a research stay, we would be really happy to welcome you here in Spain. So now going to the outline of this webinar, I hope we'll have time to go through all of these sections, but okay, I will start with a brief overview of the industrial plating processes, just to give you a flavor of this. Then we'll talk about the key phenomena in electrodeposition and the factors that we need to consider when scaling up the processes. Then I also picked a couple of case studies, which I hope will be interesting for you. So this is the electrodeposition on plastics, composite electrodeposition, and one of the use cases from the NICKEFFECT project is electrodeposition of nickel tungsten on cloth. I would also like to give you some literature recommendations, and I prepare a short training section, which I hope will be fun, and we'll finish with question and answers. Okay, so I'm aware that you're familiar with the electrodeposition technique and you know a lot about this process, but just to set the ground, no? The electrodeposition is a process which relies on the use of electric current, which passes between the 2 electrodes immersed in a solution that contain the metal ions that we want to be deposited on the surface of one of the electrodes. And let's be practical from the beginning. So our objective here is to take control over the metal deposition process to enable the fabrication of a coating with the desired functionalities, with the properties that we want, that we need. These properties can be different. It can be, for example, aesthetic, not just to improve the surface properties, or we can also develop some new functionalities for the given products, like wear resistance or catalytic activity. Usually we work with metallic substrates, no, because we need the substrate to be conductive for electrodeposition, but also I'd like that you know electrodeposition on plastics is a very highly demanded industrial process, and we'll see this in a little bit more detail in a case study. So what are the industries that take advantage of electrodeposited materials? So these are all of these here. Mainly it's automotive, electronics, jewelry, but also other ones like aerospace, defense, machinery, hydraulic, and also the renewable energy sector make use of electrodeposited pieces. Now, this is the construction of the typical electrodeposition cell. Again, I think that there is nothing new here for you, but okay, we need to have an electrolyte, no, that contains the metal ions to be deposited. The part that we want to coat is the cathode, and this is where the reduction processes will take place. Then we need to have a counter electrode, an anode that can be either soluble or inert. Maybe the first difference that we see here compared to the lab is that there is no reference electrode in the majority of the industrial electrodeposition processes. And finally, we would also need to have a power supply that will allow us to apply the electric current. So again, I think that you are very much familiar with this construction, but let's have a look at how the electrodeposition cell actually looks like during the industrial electrodeposition processes. I picked here a couple of examples. The most common processes, the most widely adopted in the industry, and the first one is the rack plating method. So in this method, the metal part that we want to coat is like hung on a hook, on a conductive hook that also provides the necessary electric contact, and then the whole thing together. So this holder is called rack. So the rack with the pieces is immersed in the electroplating solution for electrodeposition and also passes through all of the steps that are required. Then the next one is the barrel plating or the mass plating. So this is a very common electrodeposition process, which is widely adopted for coating small parts, like for example, screws, bolts, or nuts. And in this method, all the pieces are placed in a barrel kind of container, like this one, typically made of plastic. Inside of this container, there is a metallic rod. Actually, you can see it here on the video. And then the barrel rotates, the pieces tumble, and then they ensure that there is a constant homogeneous current flowing through the whole pieces. Finally, continuous plating. There are different types of continuous plating, but in general, it involves the movement of the substrate through the plating bath, as shown here in the video. It is very common for example, producing printed electronics. And another way that you may be familiar with, it's the fabrication electrodeposition of the copper substrates for lithium batteries, copper foil, which is produced in this configuration. So here we have like a titanium drum, which acts as the cathode, and then here at the bottom we have the anodes that match the shape of the drum, of the cathode, and then during the electrodeposition, the copper is deposited on the rotating drum and then just being peeled off and rolled in a form of this kind of form. So yeah, as you can see, there is quite a significant difference between the laboratory cell that we use for electrodeposition and the electrodeposition cell employed in the industry. But now the question is there a difference in the phenomena that occur during electroplating? And I'll give you the answer right away. It doesn't really matter if you are plating in a small laboratory cell or in a huge industrial tank. The key phenomena of electrodeposition will remain the same. The scale may change, but the science doesn't change. So this is one of the main messages that I want to transmit today, is that all the science that you are understanding now in the lab, it has a practical application. So what exactly are the phenomena that occur during electroplating? Here again, I'm not sure how far you went with the understanding of this process during your course, but in general, when we talk about electroplating, we have to think about the electrocrystallization phenomena. Now, this includes various stages. First of all, we know that the metal ions are present in the solution in form of the solvated or complexed ions. And then as soon as the electric current is applied to the system, these species become oriented towards the cathode. And then when they reach the interface with the surface, the absorbed species receive electron, they become reduced to odd atom. These odd atoms sit on the surface, but then they can also move around trying to seek for a more energetically favorable site, forming clusters or nuclei. And then as soon as more odd atoms join, these crystals grow, eventually forming more large structures. So then back in the days, in 1960, there was an academic researcher, René Vinand, And as a curiosity, I didn't know that, but I realized that he was actually working at Free University of Brussels, not the VUB, but the other one, the ULB. So back in the days, he proposed a diagram that you see here now on the screen. This is a simplified version, but this diagram can actually predict the properties of the deposit as a function of two parameters. One of them is the ratio between the current density to the diffusion limiting current density, which basically reflects the degree of the mass transfer control, and also the inhibition intensity, which is in fact related to the bath chemistry, or specifically to the presence of some anions, for example, in the bath that can be absorbed on the surface and then slow down the surface reactions. So as an example, no? So if we have a sufficiently high current density, good mass transport, and quite high inhibition intensity, then we can obtain very small, very nice compact, very small crystals and very nice compact coating. But if we work, for example, in this region with very high current density and low inhibition intensity, then we will obtain more like field-oriented isolated crystal structures, or even dendrites and powders. So even though this diagram was proposed so many years ago, it still remains very practical for predicting the properties of the deposit and for controlling the electrodeposition processes at any level. Now we actually see that there is there are a lot of phenomena here. No, there is the mass transport, there is charge transfer, nucleation, growth. And all of these will eventually influence the structure and properties of the electrodeposited coating. Good that we know now how we can control of these, because especially at the lab we can control the current density, the formulation of the electrolyte, which includes the salt concentration, additives, pH of course, temperature for sure, and the hydrodynamic conditions. So in the lab, well, I don't want to say that it's easy, it's not easy, but we have a very good control over all of these factors because we work with reference electrode, we have double jacketed cell, we can use magnetic stirrer with a controlled rotation speed and so on. But what happens when we do a scale up? So there are quite a few factors that we need to consider for the scale-up of electrodeposition process. I grouped them in 6 different categories, and the first one, let's say it's quite obvious. This is the electric variables. Because, why it's obvious? No, because current is actually the driving force for electrodeposition. So we can work with either galvanostatic conditions or potentiostatic conditions applying constant voltage to the cell. But in this case, there is not a lot of parameters that we can change. Basically, this is just current density and the time. And then we consider that under these conditions, the process is steady. So the reactions at the electrode and also the electrolyte remain practically constant. What we can do is, instead of working under direct current conditions, we can apply pulses. So during the pulse plating, the current is alternated. So we can combine the pulses with the cathodic current density with basically zero current, as shown here, T off, or we can also alternate pulses of the cathodic current density, but of different intensity. And what we can also do is to switch the polarity of the pulses, so alternate the cathodic pulses with the anodic pulses. This is such a great tool to control the electrodeposition process because there are different processes taking place depending on which pulse shape you are applying. So we can effectively discharge the double electric layer. We can also change the ion concentration at the electrode and this way control the reactions happening at the electrode. This helps us to solve several critical limitations that we're having in electrodeposition, for example, the edge effects, the poor coverage of the substrate, high internal stresses, hydrogen embrittlement, and even sometimes the pulse plating can substitute the additives in the bath. Okay, the next group of factors that we'll have a look at is related to the electrode variables. Here, yes, just to tell you that if we go to the scale up, most likely the geometry of the piece that we want to code will have whatever shape, but it will not be flat. So the problem is that the electricity will always follow the path of the least resistance, and it means that different areas of the complex geometry sample will experience different current densities. So generally, the peaks or the edges receive higher concentration of the current lines, and the current density in these zones is higher. Likewise, corners or valleys or more like interior pieces of the components will experience lower current density. So then the variation in thickness, for example, of the deposited metal can be sometimes a factor of 10, which is, of course, not acceptable for the industrial plating. So if we just try to analyze all the factors that will affect on the current distribution here, so this is obviously the geometry of the system, the conductivity of the solution and the electrodes, the hydrodynamics is critical, but also another factor that may not be so obvious, but it has a great importance is the surface preparation, because for the electrodeposition we need the surface to be clean and well prepared for the specific process, because this eventually will also affect on the activation potential and the distribution of the current all over the electrode. So which solutions do we have? First of all is the design of the rack that has to be tailored to the specific shape of your electrode. We can also use the auxiliary anodes and play with the anode geometry and also the anode cathode distance. So here in the schematics, you can see how actually the deposit growth in the function of the position of anodes. Of course, the agitation is important. Again, we can play with the pulses of current and also with the presence of additives in the solution. Okay, the next group of factors are related to the electrolyte. Yes, if we do again a parallel with the laboratory scale electrodeposition, then honestly we don't really care about the electrolyte, right? We can control the temperature, we can control the pH, this is something that we know, but we don't really try to maintain the solution. So it is just replaced from time to time, and not every batch or every day, every now and then, no? However, in the industrial electrodeposition process, we need to have a continuous monitoring and maintenance of the electrolyte to ensure consistent performance and reproducible results. The thing is that during electrodeposition, the electrolyte is kind of dynamic, no? So there is a consumption, a reduction of the metal species on the cathode. There is the oxidation of other species on the anode. So there are also some local changes in the pH. So all of these will definitely affect the chemical species distribution present in the electrolyte. So if at some point there is a disbalance and all these species in their concentration, this will eventually shift the equilibria and change the deposition mechanism. And as a result, the process will not be that controllable anymore. So to tackle this issue, most of the, or I know many of the industrial pilot lines, they are equipped with automatic analytical systems that can perform the analysis for the specific components, do the calculation, and then readjust the solution. So everything can be programmed. But the drawback of this is that these equipments also need to be monitored. So we need to check what exactly the system is doing. So sometimes we just prefer to do the analysis manually. Most of the time we work with volumetric analysis like titration for metal determination and XRF. Additionally, to tackle the bath impurities issue, we usually install some filtrating systems in the tanks for electrodeposition process. Now, talking about the impurities, but in general, about the evaluation of the electrolyte performance, there is a very practical, very useful test that we commonly employ in the lab is the whole cell test. Basically, whole cell is a small trapezoidal cell with this unique geometry, particular design. So in this cell, the cathode is not placed parallel to the anode. It is placed at an angle, which allows to simulate different current density across a single cathode. So we have here a region with higher current density and here a region with a lower current density. So actually we can even calculate what is the current density in each point based on this equation. So this cell allows us in a single design, in a single experiment, screen the current density range, also optimize the additives just by visual inspection of the material, also check the impurity effect and have an idea about the micro-throwing power, among others. So here is an example of the whole cell test to study the effect of the metallic contamination on electrodeposition of chromium from chromium-free bath. So you all know that chromium should have like a gray color, no, in appearance, but here on purpose we add some small contaminations of metallic ions in the plating bath, and you see that in all cases we obtain black and like powdery like deposit with almost no thickness. We can also see that at higher current density region it seems that the system is less sensitive to the presence of the additives, but also I have to say that the morphology was different in these cases. And then we see that at low current density region there is virtually no deposit, meaning that the throwing power of the electrolyte is not as good as it can be. And if we make electrodeposition on a complex piece, most likely we'll have a large variation in the thickness. Okay, the next group of factors that we'll have a look at is the mass transfer. Mass transfer is such an interesting and at the same time complicated thing because the mass transport conditions determine the growth and the morphology of the deposit. I'm sure that you are familiar already with the three main mechanisms for the mass transport, and you know the difference among them. So there's the diffusion, migration, and convection. So here the question would be how we can control all these mechanisms when we do the scale up or electrodeposition at large scale. No? So if we talk about the diffusion, it is considered as the, well, generally, no, as the main mechanism responsible for the movement of the electroactive species. So if we want to get a control over the diffusion, we need to get the control over all the process parameters like the current density, temperature, pulse shape, and everything else. Migration. Usually we can control the migration by adding or using supporting electrolytes, for example, sodium sulfate, because roughly speaking, it is considered that these electrolytes don't participate directly in the electrodeposition mechanism, but they can greatly improve the conductivity of the solution. And the convection, mass transport by convection, we can control by steering, by agitating the electrolyte. Again, if we draw a parallel with the laboratory scale electrodeposition, then usually there is no problem to steer the electrolyte. But what happens at the large scale? Because, well, here we can't use the magnetic steerer to move 1000 or 100 liter of the electrolyte. So here we have some other tools. And one of them is the electrolyte recirculation. Here, for example, you see this tank, you see this pipe here, which is indicated with an arrow. This is actually the inlet pipe. This is from where the electrolyte is returned to the tank. And here, in this part, you won't see it, but at the bottom of the tank, there is a hole. So the electrolyte is just being recirculated from one point to another, passing through the filtering system. And this way we ensure a homogeneous movement of the electrolyte inside the tank. This way actually has another objective because this piece here that you see is the heater which is used to heat the solution, to control the temperature. And you can imagine that the temperature here around the heater may not be the same as, for example, in this part of the tank. So by using the electrolyte recirculation, we also ensure that the temperature distribution inside the tank is homogeneous. So another way to steer the electrolyte is to use air bubbling. So for this, we install a system of the pipes at the bottom of the tank. And then, the air passes and the bubbles provide the mechanical agitation to the electrolyte. Another very useful tool and very practical is the use of the Venturi nozzles. So these are the small parts that you see here at the bottom of the tank. They can be also positioned at different angles, in different places of the tank, and this way giving us even better control over the hydrodynamic conditions and generating a strong recirculation within the electroplating tank. Apart of moving the electrolyte, we can also move the cathode. So it can be moved either horizontally, as you can see here on the video, or in some cases we can also move it vertically if this results to be more practical. So, okay, we have checked already 4 main groups of factors, and I think they were quite also obvious for you, because this is something that we deal with also at the laboratory scale. But the next one is related to energy transfer. And when we do the scale up, when we go to electrodeposition at large scale, the energy transfer becomes extremely important. So we need to make sure that all the metallic parts which are used in the setup have good conductivity, starting from the racks, which are used to support the sample. And here, for example, we also need to think that maybe we need to make several contacts to the sample, not just one, to ensure that the energy is transferred efficiently. Also, the bus bars, these are these rods, the copper rods here that you see on the image, also marked with an arrow. They have to be made of a very highly conductive material. Usually it's copper, but it can be also titanium or stainless steel in some cases. And importantly, they need to have a sufficient enough section to minimize the Joule heating effect. This also refers to the wires, because not every cable, every wire can be suitable for electrodeposition at the scaled up level, because again, everything that is lost due to the heat dissipation is the energy that results in the reduction of the process efficiency. Additionally, it can be simply dangerous due to the overheating. Then we also need to check the rectifier power, the power for heaters, and make sure that all connections are in good conditions from the beginning and until the end of the electroplating. So finally, we arrive to the last group of factors. You can take a moment to think what it can be before I say that this is external factors. So the external factors in general, now we can say that it can be anything that we haven't mentioned before, but specifically there are a few. This is first the external temperature or pressure, humidity, external conditions, that become extremely important, especially when the process is interrupted, for example, over the weekend or for holidays, or I know you repeat this process in summer and then in winter. So all of this may have an effect. And another issue that we have here is the so-called drag out and drag in. Both of these factors are related to unintended transfer of the solution between the process bus. Here in this video, you can see a rack which comes back after the whole electrodeposition process steps were completed, and it just flies all over the tanks that were used for this process. You can see also in these schematics here, that generally industrial electrodeposition processes involve a lot of steps. And then during the drag in, a part of the electrolyte from the previous tank can be transferred to the electroplating solution. So this way we can have an agglomeration or accumulation of the impurities in the solution. And the drag out is referred to partial loss of the electrolyte when the rack, or in this case, in the schematic, it's a barrel, is moved to the next step. So good. We went through 6 different categories of the factors that can affect the scale up of the electrodes. These were the electrolyte variables, the electric variables, mass transfer, geometry of the electrode, transfer of the energy, and all the external factors. So now we'll go through a couple of case studies and see how all of this actually works in reality. So the first case study is focused on the metallization of recycled plastics in an automated pilot line. So here, in general, the objective of this project was to deposit chromium from chromium 6-free bath onto the surface of the plastic. But obviously, the plastic needs to be metallized previous to electrodeposition of chromium. And this was one of the main challenges here, because the plastic needs to receive a proper treatment. It has to be modified to ensure that the mechanical adherence of the metallic layer is sufficient. So to achieve this goal, we designed all these steps. It's a multi-step process after all, just to pre-treat properly the plastic surface. In fact, here you can see different steps related to the cleaning, to activation, to metallization of the plastic surface, and also some steps which are related to the rinsing, because indeed in industrial plating, rinsing is considered as one of the steps in the process, because first of all you need to have all the infrastructure for this, but also it helps to minimize the drag-in effect. So I think overall there are like 90 steps only for the pretreatment of the substrate here. And then this process was employed at CIDETEC in the automated pilot line, which you see here. Another issue that we need to consider is that it is not only the bath for electroplating that needs to be controlled, but every step needs to be optimized, monitored, and controlled during the scaled up electrodeposition process. So for this, we used also the automatic control system. And here, for example, in these images, you can see already the metallized pieces that have this beautiful copper coating on top, and they are now fully prepared for the electrodeposition of chromium. Okay, the next case study that we will have a look at is related to electrodeposition of metal matrix composite. And as an example, we'll have a look at nickel alumina composite deposition. So I think that you know that composites now usually consist of the metallic matrix and then some small particles which are embedded into it, and they can provide some additional functionalities to the coating. So here we first optimized the whole process at the laboratory scale. Now everything worked perfectly, and here we also have the TM image of the alumina nanopowder. So what is the main challenge here when scaling up this process? Of course, trying to maintain the particles in the suspension and avoid their agglomeration. And then we also want to make sure that all these particles during electrodeposition are homogeneously distributed inside the metal matrix. So to tackle this case, we designed the tank. Specifically, the bottom part was made at a certain angle. No, it was not flat, so that the particles don't accumulate simply at the bottom of the tank, but they tend to be accumulated in a specific part of the tank. And then in this region, we install a propeller. So this propeller, when rotating, just lift the particles and return them into the electrolyte, no, into the plating solution. We also used here a system of pipes for the air agitation and installed this piece here for the ultrasound agitation, because it turns out that indeed the US agitation helps a lot to achieve a uniform incorporation of the particles by breaking the agglomerates. Additionally, we also installed here a recirculation system to enhance the movement of the particles, which are collected at the bottom of the tank. And note that in this case, there was no filtering system, because obviously the particles would be just stuck there in the filter. And okay, the third case study here is the scale-up of nickel tungsten porous electrodes for catalyzing hydrogen evolution reaction. So here the scale-up was made in several steps. We started developing these coatings at the laboratory scale in a standard 3-electrode cell using flat substrates. This was the work done at UAB. And then as soon as the properties of the nickel tungsten were optimized, the process was transferred to CIDETEC for the scale-up. So then we maintained the bath composition and also the optimized bath parameters like pH and temperature for electrodeposition, but also made quite a few significant changes to the process. First of all, we changed the substrate because we wanted to deposit these active materials on the porous structures. We switched also from galvanostatic to potentiostatic mode and removed the reference electrode. Then at the next step, we started incorporating all the pretreatment steps for the carbon cloth. We worked also with the holder design. I think that maybe in the following webinar that will be given by Elsica, they will talk a little bit more about this, but I'm not sure. Yeah, I hope so. We also optimized here the electrodeposition conditions and started employing all the bath maintenance protocols that we developed previously. Finally, at the large scale, at the pilot line, we had to modify again all the plating infrastructure, position the electrodes, and finally validate the performance of the final electrodes made of nickel tungsten. So here specifically what I wanted to highlight is the issue we had with the anode selection. Because, well, we started with the using of nickel anode, which is a very common industrial acceptable electrode for nickel plating. However, instead of maintaining the nickel concentration constant during the bath operation, we realized that actually there is an accumulation of the nickel ions in the solution. And indeed, the thing is that the current efficiency of nickel tungsten electrodeposition is very low. So we were actually dissolving much more nickel from the anode than depositing nickel on the cathode. So you can also see that the solution was getting more like intense color. So we said, okay, then we have to switch to an inert anode. And we tried kind of stainless steel anode that in fact previously was already used in CIDETEC for another industrial nickel tungsten plating, and it seems that everything works fine. We have a reduction in nickel concentration, tungsten concentration, boric acid remains at the same concentration, which is great, until we realize that the bath starts to change color. And also we measured at some point up to 2% of iron inside the deposit. So what happens? The thing is that deposition on the substrate like carbon cloth requires the application of quite a high voltages to overcome the resistance of the substrate. And eventually the voltage that we were applying was higher than the breakdown voltage of the stainless steel. So at some point, the anode was not inert anymore. So there was iron leaching from this electrode. So then the last option we tried, and it worked well for us, was the use of platinized titanium mesh. So here indeed we see that the concentration of both metals is decreasing. Boric acid is maintained at its initial concentration, so all good. And also the aspect of the electrolyte doesn't change, no? Or I know it changes, but it changes in line with our expectations. What is the problem or what is the disadvantage of using these anodes? First of all, is their extremely high price, because especially if we think about the industrial application where we need large electrodes, but also during the electrodeposition, when we use the inert anodes, there is an oxidation of the complex reagent happening. And in this case, unfortunately, we couldn't find a suitable analytical method for the gluconate oxidation. So we believe that it is happening there, but we can't really control it. And finally, also when we use inert anodes in electrodeposition, at some point we'll get an accumulation of anions in the plating bath, which sooner or later will start affecting the properties of the deposit. So okay, that was the main part of the webinar. Just want to make like a wrap up and summarize the main messages that I wanted to transmit here. First is that for electrodeposition, the scale may be changing, but the electrochemical principles will stay the same. So the electrochemical phenomena don't change. It doesn't matter at which scale you're plating. Second, electrodeposition step is just the tip of the iceberg, because all the industrially scalable and applicable electrodeposition processes is a multi-step process. And each of these steps will eventually affect on the final properties of the deposit that you are developing. And finally, every process has its own story. So if you have optimized the rack design for one system, most likely it will not work same well for another system. Or as it happened with the nickel tungsten case, no, the anode that perfectly works for nickel tungsten electrodeposition at industrial level for one type of anode, for one type of substrate, sorry, didn't work at all for the carbon cloth substrate. And okay, so with this, some literature recommendations from you. These are the books, which, I mean, all of them are quite basic. These ones are, like for everyone who wants to work on electrodeposition. It's the most basic book among all of them. This one is more practical. It also has sometimes some questions, glossaries, some other things, and focused more on, for example, plating of the metals, the industry, and an overview of these technologies. This one is very nice. It emphasizes the applications, the electrochemical applications at industrial level, and not only electrodeposition. This one I recommend because it was prepared at AutoTech. AutoTech is the company which is dedicated to the formulation of the electroplating baths, industrial baths. So it has a very nice practical angle for electrodeposition. And this one is for everyone who is interested in pulse plating, because there is so much you can learn about the pulse plating. So this book could be a nice beginning for you. So now we approach the very end of my presentation. I think that we're running out of time, but I don't know if I can take another like 3 minutes to go through the training section. Is that okay? Yes,
please go ahead.
Yeah, because I mean, this is definitely, I mean, obviously this is not an exam or nothing like that, but I just prepared a couple of questions for you, because I thought it can be interesting that you just, think about them, think about these issues, that they are happening, they are there. So the first question is related to electrodeposition mechanisms, because we know this is not the very basic of everything, that during electrodeposition there is a reduction of cations on the cathode. However, in some industrially scaled systems, we know that the metal ion that we deposit is present actually in the form of a negatively charged metal complex. So this is a case for example, gold deposition from cyanide solutions, solutions, or platinum from chloride complexes, zinc from alkaline solutions, and even the case of the nickel tungsten. So the first question is why and how the electrodeposition from an anion is possible. I think this might be a very easy question for you. Then the next one is related to the growth of the dendrites, because yes, usually it is not desirable, no? So it's an artifact which arises due to the uneven current distribution. So we have all these dendrites at the edges of our pieces, no, forming. However, in some applications, we can take advantage of a high surface to volume ratio of the dendrites, and for example, in catalysis, no, and we want to control them. So if we were to control the growth of the dendrites all over the electrode surface, what would be your strategy to do that? So the dendrites have to be stable and homogeneously distributed, not only concentrated at the edges. Okay, so this is the question number 2. And the final one, again related to the NICKEFFECT, nickel tungsten alloy electrodeposition on carbon cloth. So here, look, at the beginning, when we just started with electrodeposition, we obtained very nice coating on the fibers, no? At least looking at the images here. And then as soon as we do the durability testing in sulfuric acid, applying negative current for 3 days, we see that the coating just is fully degraded. And one can say that, okay, this is something that you can expect, from nickel being in sulfuric acid. Not that easy, because then we optimized the electrodeposition process of these materials, and we could maintain the integrity of the deposits, not only up to 3 days, but even after 7 days. There are some signs of degradation, but this is another story. So the question to you is, what do you think is the reason for low stability of the electrolytes from the first batch, and what do you think were the steps that we introduced for the optimization of electrodeposition that could help us to maintain the integrity of the coating during this kind of test? There was no change in the composition of the nickel tungsten coating, and also the bath formulation was not changed. So, okay, that was the end of my presentation. Again, if you want, we can discuss these questions now, or you can just contact me later by email with your thoughts, and we can continue the discussion. So thank you very much for listening.
Thank you very much, Aliona, for the nice presentation. Now I will open the floor for a question as well as for answering her question. So the floor is open. Any question, or anyone would like to answer her question? Sure, please go ahead.
Thanks for your question. Can you hear me?
Yes, yes.
Okay. So I have a question regarding in the diagram. In the diagram, you mentioned the inhibition intensity. What is that term, actually?
Yes. So, I mean, it's not a numerical factor, in fact. So inhibition intensity is related to the bath formulation. So there are some ions that can inhibit or accelerate the electrodeposition process due to their absorption properties. For example, if we have some organic additives, like, for example, PEG, in the solution, this one commonly acts as an inhibitor. So it likes to be absorbed on the surface, and then the whole electrodeposition process is kind of like slowed down. But then, for example, the chlorine ions, they typically act as accelerators for electrodeposition. So if you check the original work of Vinand, it is very well explained there, because it's kind of empirical, this value of the inhibition intensity. But not only the formulation of the electrolyte plays a role here, but also the type of the surface, because some metals can absorb, the species more readily than the other ones. But yes, again, it's not a numerical factor.
Yeah. Thanks.
Great. Thanks.
Maybe I can try answer the third question.
Please go
The
ahead.
third question, okay.
Yeah, I already forgot a lot, the first two, so the third question, did you try the pulse deposition or something? You improve the nucleation process, have a better nucleation to have a smooth surface? Because you didn't change the electrolyte, right?
Right, we didn't change the electrolyte, but it was not pulse plating. The nucleation is changed, but not by pulse plating.
You're just a higher potential.
You're on the right way. You're on the right way.
Okay.
Thank you so much for this nice presentation. And I'm actually working on the electrodeposition of zinc, but I'm looking at the anode. And I had a similar problem. I think maybe you have adjusted the current density. Because, for example, in my system, when I increase the current density, then I get the layer detached from the anode. That's one of the issues, for example, and also the porosity of the deposited layer. So adjusting the ratio between the side reaction and the main reaction.
Yes, that's true, because I mean the porosity. I think that yes, it's likely originating from the deposition conditions that you're using. But if you have a bad adherence of your coating, check the surface preparation, because very often, and this is actually the answer for the last question, the bad adhesion is originating from the poor surface preparation, because simply there is not enough mechanical force to keep the coating on the surface.
So much. Well, in my system, actually, the samples are prepared the same way, and the only difference between them is the current density. So I think it has another mechanism.
Current density should be there as one of the main factors for sure.
Great. Another question, or would like to answer the rest of the question? But
I have just a question. So in CIDETEC, you're mainly focused on doing experimental research. So for every system, as you said in the third conclusion, every system is different. You work with different partners also to model certain.
Yes, actually, at CIDETEC, we don't usually work on modeling, but in many projects, and including in the NICKEFFECT, we work with external partners who do the process modeling for us. And I have to say that it's such a powerful tool for scaling up the electrodeposition processes. It's amazing because you can speed up the scale up in I mean factor 5 or 10, I don't know. So we really like to work with partners indeed who can do the modeling of the electroplating systems for us.
Yes. And do you also model the dendrite formation?
If we model what?
The dendrite formation?
No, we don't.
Do you think that is possible, or?
It can be a nice topic. Yes. But maybe I can't say too much because I'm not working on the modeling. But yeah, I think it can be a very nice topic. I mean, we can, how to say it? We can foresee, no? We can guess in which conditions the dendrite will form, based on the conditions that we apply and the formulation of the electrolyte that we have. So we can check the formulation and say, okay, I think that under this condition we are going to have the dendrite formation. But to really model it, this is out of my control. But I think it might be possible, of course.
Okay.
And it can be very interesting.
great. Any further question from online as well? People from online, do you have any question for Aliona, or would you like to answer some of the rest of the question?
You can send me your answers later by email. I don't mind.
Any further question from the room?
Maybe the second question is about dendrite of copper, right?
Well, yes, I took one example from literature because I'm sorry, I just didn't have time to take a photo from the real piece at CIDETEC, with the dendrites. So the one on the left, yes, is taken from literature, and I think I also placed there the reference. But the one on the right, yes, it's another metal. It's tin actually. It's tin dendrites that we managed to control at CIDETEC. Yes, the other one was copper.
The problem with dendrite growth is normally diffusion problem, right?
Right. It's not only the diffusion.
Also kinetic is also, yeah, because I work on the lithium ion batteries. For lithium, it's also,
Yeah.
lithium is so reactive, you cannot kinetically control it. So it's both. It's very complicated system to control. But
Yes.
One of the ways to play with the electrolyte formulation, try to inhibition the process, make it more controllable.
Yes, yes, I absolutely agree with you. Yes. So I think that yes, maybe for you it could be also very interesting to read the original work of René Vinant, because he's talking a lot about the conditions leading to the dendrite formations in different systems.
So let's finish our scientific session now, and let's thank Aliona once more again. And thank you very much for the insightful presentation.
Yeah, thank you very much to all of you. Okay, bye.
So much, Aliona.
Bye.
Remember it.